Hello, everyone. Welcome to section 1.2, position time graphs and uniform motion. First off, we'll start off with a couple of definitions. The first one being velocity, and we've kind of already talked about this one, but really it is a change in position over time. And so this change in position can also be seen as a displacement. That's just a change in position. Now, if something is moving in uniform motion, it is moving at a constant velocity. Which means both magnitude and direction. Now, so if something is going 2 meters per second east, if it's moving in uniform motion, it is always moving 2 meters per second east. But that can also include something at rest, which means that it is not moving or stationary. So not moving / stationary. You could also say that's a v is equal to 0. Now, the formula that we have on our formula sheets shows a delta v with the arrow indicating direction, or a vector, is equal to delta d over t, delta t. Now that little delta simply means change. And you'll see that often on your formula sheets and things like that. So you'll see delta, delta, delta. That just means a change in velocity is equal to a change in displacement over the change in time, right? So where v is velocity, standard units, meters per second, d is displacement, standard units, meters, and t is time, standard units, seconds. All of this is related to physics principle 0. On your data book, you've got several physics principles, and this one is related to principle 0. Okay, it's just a little thing. Sometimes appears on exams. I just kind of want to make you aware that is where you'll see it. If you can't find them, let me know. But you'll see physics principle 0 is on the operative formula sheet is equal to, or it means uniform motion. Okay, moving along, we're going to take a look at our first example, and this is a graphing example. And we've been given the time and displacement of an object that's moving at what we would consider a constant velocity to the right, meaning a positive one. Now, within the data, we're asked to find the displacement during the time interval and the average velocity during the time interval. An interval meaning between that particular row and the previous one. So we don't actually have anything for the first one because we don't have a previous section. The displacement over this time is between 0 and 0.24 meters or 2.4 centimeters. So the time here is 0.024 as the displacement. The second one will be 0.023, and that's we're taking this displacement and subtracting this displacement in order to find the displacement for this one. Continuing on, we see that we've got 0.025, 0.025 again, and 0.023 as displacements in each interval. And again, just taking a look, this interval is between this one and the 0.047. This one is between these two, and this one is between these two. To find the average velocity during each of those, we're going to take the displacement at each interval divided by the time of each interval. And each interval here is 0.2 seconds. So we're dividing each of these by 0.2 seconds. So you wind up with an average velocity of 0.12 meters per second, 0.011, sorry, I made a mistake there. Let me just grab my eraser. There, 0.115. We got 0.125, 0.125 again, followed by 0.115. Now, in the video, we're going to see this scroll up. However, we're going to be using this data to graph our next two graphs. The first one is going to be a displacement versus time graph. And so the first one will be using this data, or sorry, we'll actually be using this data and this data, not the displacement, right? So we'll be using the blue, and the second graph will be a velocity versus time graph, and so we'll be using the purple data. Okay, I won't be coming back to this each time, but this is just where we're getting the data for the points for each one of these. So we're going to draw this graph for the data that we had. Remember that we need to use even intervals. Title, use at least half the graph space. We're going to circle those data points and not connecting the dots, but putting it all together in a smooth line. So our first graph is going to be the displacement versus time graph. Displacement, MENT versus time. So displacement will be on the x-axis here, or y-axis here, sorry. Meters. Time is going to be on the y-axis. Now, given our data points, we're going to simply make every 4 equal to 0.2 seconds, and that should give us most of what we need here to spread out our data. Our displacement, we're going to just make each of these equal to 0.01, and I'm just going to mark each second one here, 0.06, 0.08, 0.10, 0.12, 0.14. Okay, plotting our data points, the first one is at 0, 0, which is here. The next one is at a time of 0.2, and we've got a displacement of 0.024. Next one we've got is 0.4 at a displacement of 0.047, so somewhere around there. Next one is at 0.6 and 0.72, so somewhere around here. We got 0.8 and 0.0967, so somewhere around here. And lastly, we're at 1 and 1.20, which should be somewhere around here. And next thing we're going to do is we're going to draw a smooth line. I'm going to try my best to draw a smooth line using the okay, well, I think we're just going to have to stick with that then. Okay, but your graph should look something like this. Okay, the next graph is the velocity time graph. The time will be the same. Give this a title, velocity versus time. Time is going to be the same axis because it's the same data, times seconds. 0.2, 0.4, 0.6, 0.8, 1.0. Velocity is a little bit tougher, and the reason why it's tougher is because it's all basically the same in meters per second. But in order to kind of facilitate what we've got, we'll make each one equal to 0.1, 0.01. So 1, 2, 3, 4, 5. This will be 0.05, 0.10, and 0.15, which means all the data is actually going to wind up around here. We're going to plot, because the velocity that we've got is for the interval, we're not going to do this at the beginning of the time interval or the end, but we'll do it right in the middle. And so that first one is here, halfway between 0 and 0.2, because that's where the interval is, at a velocity of 0.12. And we'll just enter in the rest of the data points at those intervals. And so this is just plotting the data that we've got, and again, drawing a horizontal line. Try again. This program does not like nice horizontal lines, let me tell you. And so I want to bring that up, bring this down. It should look something like this. Probably right along this 0.12 line right here. Using a ruler would be best. I'll highlight. We'll do that one again in red, just to make it a little bit easier to see. Again, really you should be using a ruler. I'm having a little bit difficulty with the software program, but should run something like that. Okay, right? Again, note that each point here is in the middle of each interval, not at the beginning or the end. So as we take a look at the next questions, what does the slope on the position time graph mean? What does it relate to? Well, if we take a look here, the slope is normally equal to the rise over the run. But what do we have on the rise? Our delta y, right? Well, on a position time graph, that is displacement. And we're going to divide that by time because that's on the run, which means that the slope represents the velocity. The area under a velocity time graph, well, area is representative of length times width. Well, the length is velocity multiplied by the width, which is the time. Velocity multiplied by time is displacement. And that's just a manipulation of that formula, V is equal to D over T, right? Where if you multiply both sides by T, you get displacement, right? And that's how it's relating all to that velocity formula. So really, this should be put right there. Let's take a look at a few more examples here. So that's kind of the big graphing question, but let's just take a look at what if this is all happening with numbers. After 3 hours, an object is an object's displacement is 2.60 times 10 to the 2 kilometers north, or 260 kilometers north. What is the average velocity of the object? Now, because we've got kilometers and hours, we can just find an answer in kilometers per hour, right? average velocity is equal to displacement over time. The velocity, therefore, is equal to 260 kilometers divided by 3 hours, or an average velocity of 87 kilometers per hour. Now, I know that the calculator answer is actually 86.7 kilometers per hour, but because we've got 2 digits and 3 digits, mixing the digits, we go with the least number of sig digs, and that would be 2. Taking a look at number 8, we've got something traveling at 25 meters per second west. What's the displacement after 10 minutes? Now here we're mixing seconds and minutes, and we can't be mixing seconds and minutes. It's probably easier for us to change that time of 10 minutes into 600 seconds, and we do that simply by multiplying by 60 because there's 60 seconds in a minute. So velocity is equal to displacement over time again. Now, we can manipulate this first or put in the numbers first. It doesn't matter, but I'm going to do this where we're manipulating first, multiplying both sides by t to get vt is equal to d. That velocity of 25 meters per second multiplied by 600 seconds is equal to that displacement, or an answer of 15,000 meters for the displacement. Now we could also write that as 1.5 times 10 to the 4 meters, or 15.0 kilometers, keeping it to 3 sig digs. Really should have 0 there too, for 3 sig digs. Number 9 says, how long does it take for an object traveling at 9.8 meters per second to travel 2.5 meters? Well, again, we're manipulating this formula, but really we want to get this time up to the numerator position first, multiplying both sides by time, and then dividing both sides by the velocity. So a cleaned up version is time is equal to the displacement divided by the velocity. That displacement was 2.5 meters divided by the 9.8 meters per second, and we wind up with a time of 0.26 seconds. Now, notice that this is scalar, where the other two are vectors. So even though we've got a direction here, you're not saying that it's 0.26 seconds west. It's scalar, no direction. Also, just take a look at the units here. We got meters and meters per second. Meters are canceling out, leaving the seconds, moving on up to the numerator position. All right, give this next question a try. Number 10, pause the video, give this a try, and then unpause, see how you did. Okay, so answer for 10A is 9,300 meters. We're taking the velocity and multiplying it by time for that first section. The second section, the displacement is 6,300 meters, 7 times 900. And the velocity, average velocity over the entire 46 minutes is 5.7 meters per second. Now, all of these are in the direction of travel because we're not told specifically what it is. We're just going to put that in order to satisfy that. Ideally, we would have traveled this, and we'd be told, let's say, for example, that this was west or whatnot. So whatever direction this would be the direction that we should be putting this in. Okay, a couple of things to remember is that your solutions need to, first of all, communicate your answer. You need to have the full answer and the logic for finding your answer. Now, whether that be through a graphical analysis or showing your work or explaining why the answer is 0, etc., needs to be in there. Proper physics conventions that will include arrows over variables, positive and negative signs for east and west to indicate direction, showing proper formulas, using appropriate variables would be in there. An answer should be rounded to the same digits as the question, but you only round in that final answer, don't round before. Hope it helps. If you've got any questions, let me know and have a great day.